Um, so what I want to tell you about today is I want to start with this analogy of which, hang on, yeah, there it is. An analogy of the Magnus effect that occurs in optical tweezers. And it has to do with polarization gradients in a focal plane that gives you spin-dependent displacement and transverse forces. And then we want to use this analogy, or this optical effect, to make a new type of quantum gate for trapped ions. Okay, so that's the layout. And now, of course, you all know the Magnus effect. If you've ever watched a football game and watched someone take a free kick, by spinning the ball, this player can sort of curve the ball around some obstacle, like this obstacle here. Okay, and this spinning ball, if you look at it in the moving frame of the spinning ball, there's this flow of air passing by, which is then deflected due to the rotation of the ball. And momentum conservation then tells us that there must be an opposite force on the ball, so the transverse force. So how would you do this in optics? So here's the aerodynamics version. Now in optics, what we could do is we can replace this stream of air by a laser beam, like an optical tweezer. Okay, and then right in the focus of the optical tweezer, we place a rotating dipole. So how did it get there? Well, for example, we could choose an atom that has the following level structure, so a ground state 0, an excited state of J equals 1, and separate these magnetic sublevels. We tune the tweezer close to this delta M equals +1 transition. Then this linear polarization will pick out this component and induce a rotating dipole. And now please note that I was careful to choose the quantization axis perpendicular to the plane. So the rotating dipole rotates in this plane that contains the tweezer itself. Now such a rotating dipole emits, or scatters if you wish, a wavefront that has the form of a spiral. If you look at the far field, this spiral will have a phase front that has a small tilt with respect to the one from the tweezer itself. So now you have two tilted wavefronts, and now you can imagine that if these interfere, okay, if they interfere, depending on the phase difference, you could have constructive up here maybe and destructive down there. And if that happens, the laser beam will be deflected, just like here in the aerodynamics case. And that's exactly what's going to happen. This deflection turns out to depend on the detuning. Of course, the detuning here determines the phase of the dipole, so it's not that surprising. So by changing the detuning, you steer the beam up or down. For red detuning, it's going down in this picture. That means that the force on the atom will be going up for momentum conservation. And the consequence of that is that the atom will not sit on the optical axis of the tweezer. It will be pushed a little bit off to the side. And turns out this displacement of the tweezer trap is lambda bar, lambda over 2 pi. So what we're dealing with here is a situation that goes beyond the paraxial limit. So what we all learn from the textbooks is the Gaussian beam that we all know and love, which is an amplitude that's a Gaussian shape and a uniform polarization. In optical tweezers, we like to focus the beam with a high numerical aperture to get the spatial resolution. And now we're going beyond the paraxial approximation. And then we have to deal with the fact that the Gaussian beam is not a solution of the wave equation. So what do? Instead of a Gaussian beam, we can take a plane wave expansion. You can always do that, of course, because plane waves are proper solutions of the wave equation. Oops, okay. Here's the plane wave. It has a direction k in a direction theta phi, and now we do an integral of all angles theta phi with some amplitude function, and of course it must have some polarization. And here I'm choosing the x-like polarization. I'm saying x-like because if you have different k vectors, then the polarization must of course be different. It must always be transverse to the k vector. So that's x-like polarization. I can lump these together in some vector valued amplitude function that depends on propagation direction. Okay, and we can do this now, this E of omega, for both the incident wave and the scattered wave. And then they interfere, and the interference term, which is now direction dependent, is going to be something like the product of these two E omegas. Okay, the scattered wave, coherent part of it, and the incident wave. Now, if we're interested in the beam deflection, it turns out that this interference term is the only one we need. And the beam deflection, so basically the change of the average k vector, so it starts like this and it's deflected to something else, is the integral of this interference term, and we have to basically take the unit vector in direction omega and take its weighted average, weighted by this interference term. Okay, and then once you have the deflection angle, of course you know the deflection, the change of wave vector, you know the deflection angle, which is shown here. And you see that it scales like the fourth power of the angular waist. So this W theta is basically the diffraction angle of the tweezer beam. So this tends to be a small number, and the fourth power is of course an even smaller number. What you also see is that the tuning dependence here, which is of course the force on the atom, the delta theta is the force on the atom, but the tuning dependence reveals that this is nothing but a dipole force. We recognize this dependence as we know it from the dipole force. So here's what it looks like. The beam deflection in angular units. So this is like a Gaussian-like beam, but plotted in terms of angles. And then you see that for red or blue detuning, it's shifted just a tiny bit to the left or to the right. So it's really a Gaussian beam, and it's shifted a tiny bit up or down. And just for fun, I also looked at the top hat beam, which is like a with sharp edges. It looks a bit different what happens here, but anyway, it's a small number, and the deflection is small compared to the divergence angle. Okay, but more importantly, we can use it. You can use this force that's associated with it. Okay, and for that we need to look at the focal plane polarization gradients. So what I said is that this polarization has to be different for different k vectors, and that means that you will get in the focal plane you have all these polarization components together, and so you get polarization gradients. And one way to think about it is, if this is what I found in a paper from the Luken group, if you focus down a linearly polarized light beam, then this ray here is polarized like that, but this ray is polarized like that. Now if you go away from the axis like here, this one arrives a bit earlier than this one, so the light polarization rotates from here to there, so that's counterclockwise. So I think this is probably a typo in that paper. Okay, but the idea is clear. Here's another interesting paper from a Chinese group. They also pointed out these polarization gradients in the focal plane. You can see here the colors are the ellipticity of the light, so you get an ellipticity gradient. And they showed that if you use then vector and tensor polarizabilities, that the different M magnetic sublevels in the rubidium ground states are separated in space. And they were able to drive microwave sidebands where they change the phonon number. This can only happen because the traps are displaced a little bit, so that the wave functions are no longer orthogonal. But there's a simpler way to look at all this, which happens if you decompose this field in the focal plane in transverse spin components. So now what I'm doing here is I'm decomposing the light field in circular components, but if the tweezer beam comes out of the plane, the circular components would be like this, okay, in this plane. So this is a bit unusual perhaps, but if you do that, what you find is that the Gaussian beam cross-section just splits in two, okay, and so the sigma minus component is shifted left by lambda bar, this one is shifted right by lambda bar. So this is transverse spin angular momentum, if you wish. Just for fun, I also tried it for Laguerre-Gaussian mode. Get the same idea. So this is now Laguerre-Gaussian. Added some orbital angular momentum here. But the transverse spin components are again just separated by minus lambda bar, plus lambda bar. Let's see, okay. Okay, so we have in the focal plane of the optical tweezers, where you really have two tweezers for different polarization components. Now let's take an atom which has this level structure. Spin 1/2 in the ground state and spin 1/2 up here. And now this state is only sensitive to the sigma plus component. This one feels only the sigma minus component. These are spatially separate. So that means if I have an atom in a superposition of the minus and plus state, this atom will be sort of, its two spin components will be spatially separate. Yeah? Like this here. Their separation will be lambda over pi, plus lambda bar, minus lambda bar. Now what if you take a pair of tweezers? So now we have two tweezers next to each other. Now the plus and minus states are separated by 2 lambda bar. Here's the other tweezer. And now I can even... So the thing now is that the distance between these two atoms depends on their spin states. So this is what we're going to use for a quantum gate. In fact, you could even manipulate that by rotating your quantization axis. This is what I did here. I rotated the magnetic field. This plane actually. Okay, it's the YZ plane, so it's this one. But then you can actually take these two spin components and sort of move them about like that. What if these two atoms interact? Then I can make an interaction that is spin dependent. So this is exactly what you need for a quantum gate. So then I talked to my colleague René Gerritsma, who is an expert in ion trapping. And here you see a linear ion crystal. Only 6 ions, not so many that Rainer showed us, but anyway, it's a linear crystal of 174 isotope ytterbium ions. And ytterbium, this isotope has exactly the level structure that I showed you before. So spin 1/2 down here, spin 1/2 up there. So now what we do is we take this linear ion crystal, we focus our tweezers on 2 of the ions. We want to make a quantum gate between this ion and that one. So we send our tweezer on those 2. What's going to happen now is that the 0 state, this one, is going to be pulled to the left, and the 1 state is going to be pulled to the right. Now, the ions are trapped in a pole trap, so these forces are just a tiny addition to the trapping potential that's already there, okay? But nevertheless, you can sort of nudge the ions a little bit to the side. And yeah, that means that if you do this for 2 ions, and if they are in the 0,0 state, let's say, they will both be pulled to the left. If they're in the 1,1 state, they will both be pulled to the right. And 0,1 and 1,0 are pulled either outward or inward, okay? But that means since all these ions are coupled together as a crystal, it means that this situation, the optical tweezers push the entire crystal to the left. So the entire ion crystal is pushed to the left. And here the entire crystal is pushed to the right. But here nothing happens, because these 2 forces sort of cancel. So as for the crystal as a whole, nothing is going to happen. So we have access to the common mode, the center of mass motion of the ion crystal, but only if the ions are in even parity states, but not if they're in odd parity states. Okay, so then we did some calculations. Let's see, how much time do I have? Okay, not going to go through all the details, but let's say this is a displaced tweezer potential. So it's basically a Gaussian function, but with a displacement that depends on the spin. Okay, so you do a power series expansion and you get some offset, which is not interesting. You get a harmonic oscillator term due to the tweezer potential, and you get a spin-dependent force. So the x times sigma z. Again, this is additional to the ion trap. The ion trap is dominant, but this is an addition. Then you take two ions, you have two tweezers, you get two of all that. Okay, so you get two of these terms here, two of these terms here, and then we get rid of the. We just ignore these terms because they're not spin dependent, so they're not so interesting. But what is now interesting is you can modulate the strength of this interaction with by modulating the intensity of your tweezer. So this A of t, and this allows you to resonantly enhance this kind of interaction. So you modulate it close to the trapping frequency of your center of mass trapping frequency with small detuning delta, as it's called. And when you do that, you can do a rotating wave approximation. So this modulation function is a cosine. But if you do the rotating wave approximation, this can then be rewritten in terms of the phonon mode operators. So the AC and AC dagger are creation annihilation operators for the center of mass phonon mode. Okay, then you apply a couple of more transformations. This takes out time dependence. This is called the Lang-Veershoff transformation. Let's not go into all the details, but in the end what you end up with is an effective interaction between the qubits that looks like sigma z here. Okay, and this strength of the interactions, this g wiggled squared, scales as the inverse 8th power of the tweezer waist. So we better choose a small tweezer waist to get this to work. But this is exactly what we can use now for a quantum gate, because if the two atoms are in the, let's say, the even parity states, 1, 1, then this is 1. Down, down, it is also 1, but for the up, down, and down, up, it's 0. It's -1. Sorry. So what happens then is if you modulate this tweezer intensity, is that the position and momentum of this center of mass mode goes through a loop in phase space, like so. Makes two loops because we do a spin echo sequence, but the phase that, or the area of this loop is now the phase that the wave function picks up. And then we see that this phase is picked up for even parity states, down, up, up, and down, down, but nothing happens for the odd parity states. So this is exactly a quantum gate, a geometric phase gate, as it's called. So we did some numerical simulations to see what sort of fidelity we could expect. Turns out light scattering is an important one. So this is off-resonance scattering of tweezer light. And then if we take a Gaussian tweezer, this is kind of bad, but we can do Laguerre-Gauss mode, so that the atom sits in the dark, basically, or the ion, I must say. And then this gets reduced by at least more than an order of magnitude, so that's good. We checked out the sensitivity with respect to the gated time, and we see you see there is some minimum here at 120 microseconds. Try this for different pre-cooling conditions of the ions. So there's the ground state, or let's say phonon number 0. This is Doppler cooled. This is the red one. And just for comparison, we also took a very hot ion sample. Then it goes up to 10 to the minus 3. So still not terrible, but you don't want that probably. The tweezer could be misaligned. We think that the 30 nanometers would be realistic, which brings us to 10 to the minus 3 for that source of error. Actually, this is not specific for this particular quantum gate. It's for any tweezer-based gate. You would suffer from these misalignments. There's intensity noise. That seems to be fine, because if the intensity noise is on the 1% level, then that doesn't affect the infidelity too much. So, we have an optical Magnus gate with this type of interaction. It promises state-of-the-art fidelity, possibly. We don't need to cool it to the ground state. And what we particularly like about this gate is that you get access to the axial motion of the crystal by sending in your tweezers from the side. So you get good optical access, and you can still access the axial motion. And you can access axial motion using single beams, okay? So you don't need any pair of beams, like from here and here, to get k-vector components along the axis. You don't need that, because it's the optical Magnus effect that gives you the sideways axial forces. And that's important, because if you would need counter-propagating beams, you would also need to stabilize their relative phase. We don't need to do this for obvious reasons. So that was 174 ytterbium, just for completeness. You can also do different isotopes. This one has perhaps one disadvantage, that this qubit is magnetic field sensitive. But if you go to 171, you can also choose these states as a qubits. These are so-called clock states. They're both m = 0 states. But now you have to couple them through Raman paths. And the fun thing is that now there's two Raman paths from 1 to 0, like here and here. But this one involves sigma minus photons, this one sigma plus photons. But one of these Clebsch-Gordan coefficients is negative. So these two paths interfere, they cancel, they interfere to 0. Except when the ion moves a tiny bit to the side. Because if you move it a little bit to the left, then the omega minus amplitudes go stronger, and these go weaker, and then this will win over the other path. So it doesn't cancel if the ion moves away from the axis. And the final effect of that is that the final effect is that this interaction is now not sigma z, but sigma x, sigma x. But apart from that, you can still do all the same things. So these are this is the group of René Gerritsma, and the people who are going to actually do this is shown here. They're awesome. Okay, you know this OMG acronym, right? It means Optical Magnus Gate. But anyway, what I didn't tell you about was we also have another project together with Florian doing tweezer arrays with single strontium atoms. And here we try to make them talk to each other, interact, by exciting to the Rydberg levels. So, and we're developing this in collaboration with the group of Sir Vaas Kokkelmans and Edgar Vredenbrecht in Eindhoven. Some other time. So, here's my summary. I showed you that there is this optical analogy of the Magnus effect that occurs in optical tweezers, and how you can use that to create a quantum gate for trapped ions. Thank you.
Okay, it's now open for question, please.
So, thank you. I think the idea is really appealing. What is the geometrical phase gate that you're telling us about is very similar in action to what we know from Didi's gate, the original phase gate of the Wineland group. So what is actually the advantage? Because it seems to take a little longer than what you do with the beams when you just have the moving gradient, the walking wave.
Yeah, so what we like about this gate is that the transverse, or the axial force can be exerted with a single beam. So you don't need phase stabilized counter-propagating beams. This is what we like, but it is maybe not the fastest gate that you can find. So we were perhaps a bit conservative in choosing the waist of our laser. You can still gain something there because it scales like the 8th power of the waist. So if you change it only by like 10%, you already gain a factor 2, right?
No, I really like the scheme, especially because it's good for clock states, but you can't use the geometric phase case otherwise. So for the DD gate doesn't work for clock states.
Okay.
And so this is one of the points. But then for the clock states, then you forgo, of course, the advantage of not having a walking standing wave, because you're back to Raman configuration.
Not really, because the Raman beams can come from the same direction, so you can modulate the sidebands on a co-propagating beam. Yeah.
I agree.
Yeah.
Yes, please.
So Robert, if I see it right, the size of your Magnus force is basically coming from the gradient of your intensity profile of the focus beam, which is limited by wavelengths. So have you ever thought of using some of these dark state ideas where you are living with a gradient of intensity ratio rather than having being limited by the wavelengths?
I haven't thought about it, but it sounds a very interesting idea. Yeah, I haven't thought about it. Yeah.
More questions? Yes, please.
Can you comment on the technical challenge of the high numerical aperture objective lens, and what is the typical range that you have in mind for these experiments? So I assume that you need to be very tightly focused, as you explained, and this might limit the field of view.
So the calculations were done for a numerical aperture of 1/2, so which is not extreme. But if you go to optics companies and let it design for you, I'm sure you can get to 0.75 or so. This was just sort of standard off-the-shelf objectives.
More? Oh, in that case, let's thank Robert again.